Swayam Prabha. Digital India. Educated India.
All right. So good morning. Oops. Today I'll talk about industrial robotics. Okay. Some of the general thoughts and ideas on industrial robotics, but specifically applied to machining. We're talking about manufacturing. So getting robots to do machining. That's fundamentally the idea, right? I'll talk about what makes this problem difficult. Okay. Robots by themselves are not new. Robots have been around for a long time, right? Since the 60s, actually. The earliest implementation of industrial robots in practice was in manufacturing. Even though today you hear about drones, you hear about submersibles, you hear about other humanoid robotics and all kinds of other more fancy robots, the earliest implementation of robots was actually in an automotive facility in Japan. And it was focused on utilizing the promise of robots, which is, any kind of automotive assembly, as you know, is very manually intensive, right? I mean, it used to be much more so, but it still is, where human labor is involved. And so a lot of repetitive work, could be hazardous as well in some instances. So how do you actually, free the human being from doing repetitive hazardous work? A robot is a machine, so it can keep doing this very repeatably as long as you've trained it to do that job. And so that is the earliest implementation of industrial robots. So industrial robots in a manufacturing environment are not new. And I will distinguish, industrial robots from other types of robots. Okay, I'm not here to talk about, you saw an AMR yesterday in the lab, right? Which is a mobile robot, right? That's also applicable in the manufacturing environment. Clearly, they were using it. And you saw the other robots, the blue robots, the Yaskawa robots in the lab. Those are industrial robots. That's what I mean by an industrial robot, okay? And typically, they are not mobile, although those robots can be put on mobile platforms. You can put them on that mobile platform that is moving around and take the robot to a task or to the part and perform some task on it, right? In yesterday's demonstration that you saw, the robots were being used for pick and place primarily, right? Those are some of the earliest and most common applications of industrial robots. Picking, placing, loading, unloading from the machine tending basically is what it's called. So those are all very common applications, right? But for reasons we will discuss, the accuracy requirements for performing those type of applications are not that high. Unlike machining on a machine tool, right, where you're trying to hold tight dimensional tolerances, produce high surface quality in terms of surface finish, etc., right? So, but there are scenarios where if you can use a robot to do such operations, it can be quite beneficial. And I'll give you some examples of where those types of applications are that motivated some, this type of research, the work that we've been doing for now probably a decade or so, right? Roughly that. Okay, so let's get moving. If I can, for some reason it doesn't move. Okay, there you go. So I've already introduced the problem as I've been speaking, but I'll give you some more formal introduction and then talk about the challenges for using the kinds of robots you saw yesterday, the blue Yaskawa robots. Those are 6 degrees of freedom robots, industrial robots for applications such as machining, okay? And other applications as well where accuracy is very, very critical, okay? But historically, they are not they have not been used for such tight tolerance type of applications. Okay, they cannot be for reasons you will understand shortly. I'll give you the example application that motivated our work in this area, and then I said they're not as accurate. That's why you don't use them. Well, how do you make them more accurate? So I'm going to talk about some ideas and some methods that we have investigated to address some of these limitations of industrial robots. Okay, these are current. Many of these things are current topics of research and interest. And then I'll summarize. All right, so in accurate industrial robots for manufacturing, and what you see in this image, this is what you see if you go to an aerospace company that is making parts. You can look this up on the website. This is taken from a website. Electroimpact is actually a company that makes and builds machines for manufacturing of aerostructures for major aircraft manufacturers. Okay, they're very specialized in doing that. So this is a picture taken from their website. And you see here a gantry robot, a gantry machine tool, I should say. Not a robot, but a machine tool. This is a gantry machine tool. You see the length of the structure. It's a fuselage section or a portion of a fuselage of an aircraft. Actually, this is a composite layup machine. In this case, it's actually laying a composite skin on a mold. That's what it's doing. But even though it's not doing machining here, it gives you a sense of scale of the parts and the types of machines that get used. Even machining of large aerostructures is done on such very large machines. I mean, they occupy, half the length of this building, much taller than floor to ceiling that you see here. And they cost millions of dollars, very expensive. Once you make those investments, they are inflexible. You can't move them, you have to use them. And hopefully you have enough use to justify the cost, right? But they are accurate. They're accurate, that's why they get used. Just like machine tools. They're larger versions of machine tools, but they're gantry type of machine tools, right? So that's what you see. But there are limitations, right? This is how you use. But again, there are disadvantages. If you think of aircraft manufacturing, most aircraft platforms last a few decades when they initiate a new aircraft, commercial aircraft, for example, whether it's Airbus, Boeing, whatever, Bombardier, any of these companies. They will start a program and it'll last a few decades where they'll sell these planes, right, to customers. But they can't change, for multiple reasons, they can't change their processes easily because a plane is transporting human beings. So safety is critical, right? We don't want accidents. I think, I forget, maybe Professor Samuel had mentioned that there is more deaths in traffic accidents than there are in airplane accidents. So you can think of the safety requirements, right? That's why it's like that, because we don't want to fly in a plane where I'm not sure if I land, right? That we don't want that. So because of this one reason, the other reason is because of these requirements, safety requirements, production processes, once they get designed and approved, they are set. They are not very flexible. So it's very expensive and inflexible process. But if you can replace such large machines, right? And if you were to, let's say, go to another platform, making another type of airplane now, after a few decades or a couple of decades, then you need to design an entirely new production line, right? Now, you may or may not be able to use these machines, which means you have to make another significant investment, right? So it would be nice. In contrast, serial link manipulators are in robots. Right? They are serial link manipulators. Right? They're like your arm. One link, another link, many links, right? So they're relatively cheaper, right? You can buy robots as cheaply as, I don't know what it costs in rupees today here, but maybe $30,000, even less. Small universal robots for simple tasks which don't need to carry a lot of payload can cost you as low as $5,000 to $10,000, right? Versus millions of dollars. So obviously, they're cheaper, relatively cheaper, but they're more flexible. They're reconfigurable. I can repurpose and reprogram a robot, right? I can also put this robot on a movable platform, like the one you saw in Professor Samuel's lab, right? Or I can put them on rails. I can hang them from ceilings, move them on rails for, doing tasks along a large part like you see in this picture, right? So there are advantages if I can get them to be sufficiently accurate, okay? What is the challenge? Well, one challenge has to do with challenges that you as a human being face with your arm. How stiff is your arm? Obviously, our stiffnesses all vary. Some may have exercised and have a lot of muscle and can resist more loads, right? But that, I can easily push and deflect my arm. So they're compliant. The compliance comes from the joints. It also comes from the links, your arm here, forearm, etc., right? Analogous fashion. Compliance is a problem, which means that if you use these robots to perform tasks that involve contact forces, such as machining, then they will deflect. They can also vibrate, depending on the nature of that external contact force. If it's a time-varying force, then the deflections will also vary with time, right? So they can vibrate. As a consequence, that's not the only reason. They're overall less accurate. Compliance is one obvious limitation. But the way they are constructed, especially the kind of robots you saw yesterday, the industrial robots that I'm referring to, same kind of robots, are their what is called kinematic accuracy, their ability to move from point to point at certain speeds, right? Kinematic accuracy is limited because of the way they are constructed. You saw yesterday there's belts, there are gear systems, gear reducers inside, etc. So gears, if you know gears, there can be backlash. So there are these type of error sources because of the drive systems that are used. And as a result, they all accumulate, right? And they essentially, if you were to use forward kinematics to describe what happens at the tip of the robot, the end effector of the robot, what is called the tool center point, as a function of joint kinematics, there are errors in the joint. They will translate to errors in what happens to the position and orientation at the end, right? Similar to your arm, actually, okay? So these are challenges with robots. This statistic you can take with a grain of salt. So very few robots generally, whether it's less than 2% or not, I don't know. Alex Werl is a professor at University of Stuttgart and a colleague of mine, friend of mine, and he and we participated in writing a paper, and the Germans came up with the statistic that less than 2% of industrial robots are used for machining type of applications. The only machining type of applications robots have been used for a while has been in a foundry to actually cut out flash from castings. That doesn't require a very high accuracy. It's just to remove excess material that has been, squeezed out from the mold during casting. So those type, and as well as some work on polishing, grinding has been done. It's done in industry today, but not for milling kind of operations, where you can produce complex contours that may be necessary for aircraft structures, okay? Most aircraft frames, whether metal frames or even today composite aircraft, right? Commercial aircraft have composite skins. They have to be machined. They have to be trimmed. You have to trim them. You have to cut out holes. There are tens of thousands of holes, if not hundreds of thousands, depending on the size of the aircraft, have to be drilled. And then fasteners have to be put, sealant has to be put, fasteners have to be put, and then fastened to the frame. So all of those operations, drilling is an operation. This is done today with robots in practice in the last less than a decade. So it's fairly recent, right? That is being done. They do trimming of windows. How do you think they create the hole for the window? They mold the composite structure and they cut out. right? So trimming is done, but again, using gantry type of machines or other types of machine tools, more conventional machine tools, right? So this is what you do. Now, you see here, actually, this is an example. I don't remember. This one is, this is probably a robot doing drilling. It's called the QuadBot system. And there's 4 robots that are doing drilling. But here, the robot is primarily being used as a positioner. Simply take it to where it needs to go. And then, yes, they have enhanced the accuracy of this and to drill. There's auto feed drill at the end effector and positions the robot at the right location and clamps down on the outer surface of the skin. So it gets a grip and puts the skin and the frame together, clamp down, and then drill. Right? That's what it does. That's the level of automation that exists today in practice. Well, what motivated us to actually try and say, oh, we need to make robots more accurate than they are? So here's one example. I don't know how many of you know. I'm sure if you've flown on an airplane, then you have not seen it, but you have sat on an airplane which exhibits these characteristics, okay? Most airplanes that are flying today, actually all of them, have, when they're produced, they're assembled. That assembly process is very time-consuming. For large planes, very time-consuming. It could take a few days to assemble the wing to the body, and each section, the fuselage sections, depending on the type of aircraft, are made in separate parts. There's an aft section, mid section, there's a forward section, and these are brought together and mated, right? Now, if you think of composite structures, accuracy of manufacturing is difficult. They cannot be made precisely, It's not a perfect circle, the fuselage. It's some geometry, but to control the geometry during composite manufacturing is difficult. So there are errors. So when you bring the 2 pieces together, like the wing to the body or 2 sections of a fuselage, to join them, there are gaps and there are interferences. So what do? They bring them together, they measure them with very sophisticated metrology, and, oops, hold on a second. It's changing, it's on some timer. And they bring them together, they join, then they measure them to see where there are gaps, and then they go and make shims, essentially materials that are used to fill the gaps, out of fiberglass, out of composite, out of metal, depends on what it is. And there are thousands of them on an aircraft. So you're adding mass. Okay? Now, wouldn't it be nice if now, instead of doing that, I'm adding weight, which is bad from a fuel efficiency standpoint for an aircraft, right? You use composite to lightweight the aircraft. But now you're adding more material because of your inability to produce things that are very accurate. So what would be nice? And these shims are produced in a machine shop and then brought back. That takes time as well. Now, what if, think of the scenario. So this is what I described. This is saying the same thing, what I just described to you in words, okay? So what do? What is an alternative approach? Alternative approach would be that I don't try to make my structures very accurate, which is good. It costs less to do that. Let's say I make one of the fuselage sections larger, right, than the other, slightly larger on the inside diameter, let's say, so that there will be deliberate interference. Okay? Now I bring them together, I measure to see how much interference there is. I have to do that. And then instead of going and making shims, I just bring a machine and machine it to size. So I don't need to add any new material. And I join the 2, right? So that would be called shimless assembly without using any shims. Okay? That is not done today. Okay? Today what they try to do is to try to predict the thickness variations and make shims ahead of time and then do the assembly. So this is one motivation. Now, but if I have to machine this fuselage on the assembly line for a large airplane, I can't take a gantry machine there, or I can't transport that big piece to the gantry machine, some other facility, right, where the machine tool is. Instead, if I have a robot that's accurate enough, I can put it on a mobile platform that can rise up and down. I have measured it where the interference is, and it is. I can go and actually machine it to size. That's one potential application. It's not the only application. Robots can be used for painting, for sealing, and all kinds of other applications, or trimming composite structures. So this is one motivation example. But what is the challenge? Why can't I do this today, right? All right, but to illustrate, this is a video that actually shows you what a typical robot machining shims that are attached to a model wing rib. Wing rib is a rib inside a wing of an airplane. Let's see, you can see the video. It's actually going, this is a 6-axis, 6-degree of freedom industrial robot, similar to the one you saw, much bigger, with a much higher payload, with a machining spindle at the tip, and it's machining these fiberglass structures attached to it. These are shims that minimize the gap between mating structures, okay? All right, so that is kind of the application. We want to be able to do that on the assembly line using such a robot. What makes it difficult to do today is the question, right? So robot accuracy is the challenge. You know, most people don't realize robots they think are, oh, they're very accurate, they think. No, robots are very repeatable. If you buy a robot, the manufacturer will only quote you a repeatability value. And they'll give you a repeatability value saying that, oh, it's repeatable. If you teach it to go to a certain point manually and ask it to go thousands of times, it'll go to within 50 microns of that position, which may be good enough for many applications, right? That's a good repeatability. So that's repeatability, okay? But accuracy would be, hey, if I ask it to go to some specific point in space, okay, through an offline program, how close to that point in space does it go? And unfortunately, that question, if you try to answer, most robot manufacturers will not give you an accuracy number. They cannot, because of many error sources that are there, right? Some of them I mentioned earlier on. So as a consequence, what will happen if you were to do that? The best accuracy with the best calibrated robot might be slightly less than a millimeter, a few hundred microns, if you're lucky, right? Well, that's not good enough for a machining application. If I can't position the robot precisely all along its path, that it's going to actually be programmed to cut something to within, depending on the type of application, let's say within 200 microns, 0.2 millimeters, for certain applications in aerospace maybe, or less than 0.5 millimeters, it's not good enough, okay? So repeatability is specified by manufacturers, but not its accuracy. Robot accuracy and methods to measure it are not well defined. There is a standard, ISO standard 9283, that tells you how to actually evaluate the pose of the robot, the accuracy of the pose of the robot. The pose accuracy, it is called. Pose accuracy refers to position in space, the position accuracy in XYZ, right, in the Cartesian coordinate system, and its orientation, defined by Euler angles, right, about XYZ, rotations about XYZ. So 6 degrees of freedom, you can define that pose, or you can define it in terms of joints. Remember, all the joints in an industrial robot are rotary joints, revolute joints, basically, revolute joints. So they rotate only, right? And the combination of those gives you different positions in space. So what are the problems with this? What's making robot accuracy a challenge? Major sources of robot inaccuracy are listed here. Backlash, link dimension errors, those are called kinematic errors. Compliance, we already talked about this. Static, not just static compliance, but also dynamic compliance, okay? That is when you subject a structure like a robot arm to time varying loads, right? Then, like as would happen in the machining operation, then what is its stiffness, or inverse of compliance is stiffness, right? Stiffness and compliance are inversely related. So And the one other difference, which most of you, to what extent you realize, I don't know, but unlike a machine tool where the stiffness of the machine tool in its work volume doesn't change a lot, which is a good thing, okay? Whereas with the robot, each pose of the robot it has a much larger reach than a typical machine tool, but each pose of the robot corresponds to a different stiffness. So its compliance or stiffness changes over its entire work volume. If you stretch out your arm versus like this, versus here, versus there, it's similar to your arm. Your arm is, if I do this, you push straight out, I'm quite stiff. If I do this, I'm not very stiff, laterally, right? Same thing, if I change the pose, if I do this, not as stiff, right? That's what I mean. Same idea applies to robots. That makes it difficult, which means I don't know what its stiffness is, depending on its pose. And if you're using it for machining or some other highly accurate task or where accuracy is important, then its compliance characteristics will change. Even if the external loading is the same, its deflection will be different, right? That makes it more challenging. There are other errors. Temperature variation. This is not even accounted for explicitly. Well, it's mentioned in the standard. You know, in most manufacturing environments, depending on, in a foundry, for example, in a foundry, the temperature variations can be huge, right? And so thermal expansion contraction effects can also affect the accuracy and wear and tear, obviously. Okay, so I've said these things already. So this is basically saying that if you have less kinematic accuracy than CNC machine tools, you'll have more inaccuracy of the part. Compliance, so I won't repeat all of this, let's move on. So how do we go about trying to actually address some of these limitations, right? That's what we tried to do in our research. One of the first things we did was, okay, can we compensate for the static deflection? If I were to use a robot for machining, right? Let's say I'm milling a slot with a robot, right? There are forces acting on the robot arm. Then can I estimate what the forces are? And using knowledge of the forces, estimate the deflection based on knowledge of the stiffness of the joints of the robot, and I won't teach you all of this. If you haven't learned, don't worry about it. Just take my word for it that you can use forward kinematics to relate joint compliances to the Cartesian compliance. And can I use that knowledge? If I know the force acting at the end of my arm, I know the stiffness at the end point of my arm, can I predict it? You know, you all understand F equals Kx, like a spring. So it's like a spring. I know K at this tip. I know F at any point in time and space. I can calculate X, right? F over K gives me X, correct? The basic idea is just that, right? The mathematics is more complicated because your kinematics is more complicated, okay? So let's not worry about that. So how did we go about addressing this? Now, machining is more complicated. Machining forces vary with time in a milling operation, particularly. And as you're moving, just like we were talking about micro milling, right? The milling tool moves. Your arm is changing. The extension of the arm and position of the arm in space is changing. And as I already said, the stiffness of the arm changes with its pose, right? So therefore, you have to be able to predict its changing compliance. You have to predict the forces or measure the forces somehow in real time, and then be able to estimate the deflection and compensate for it, right? So what this is showing you is our first attempt at trying to do this, okay? Using this basic understanding. Why can I do this? Because people in machining have already figured out how to model and predict forces in milling. Now, yesterday I told you that machining predictions and modeling is very complex, but I only told you about modeling trying to model the physics very accurately using finite element type of methods. But there are other methods which are semi-empirical methods that are much easier. But they cannot tell me everything. They cannot tell me the strain distributions. They cannot tell me the strain rates. All that it won't tell me, but it'll tell me the forces. And from forces, if I know stiffness, I can calculate deflections, okay? So I didn't talk about that And if you're interested in knowing how that is done, you talk to me and I'll point you in that direction and you can go read that. But for now, just accept this, that there is another way of predicting forces in milling. Is well established. There is even commercial codes available that will do this for a CAM Pro. You can, in fact, more modern versions of CAM software today, some of them already have these tools embedded. So in addition to simply simulating the three-dimensional tool path and geometry, you can also predict the forces, okay? It can be done. So using that knowledge, if I want to move this robot to some desired position in space, right? I can basically, let's say, determine the forces somehow, right? I can measure the forces. If I measure the forces somehow, I can use the measured force and this model that says milling force as a function of cutting conditions is this. That's the model that I briefly mentioned exists. I can invert that model and determine, when I'm measuring the force, when the force is this much, how much is it really cutting? What is it cutting? How much is the depth of cut? Axial and radial depth of cut. And I can take that information and check against the nominal, what it should be. See, what will happen because of deflection? When I'm trying to cut a certain axial depth and radial depth at a point along the tool path in milling, if there is compliance or deflection, I'm going to cut less. So what would the force be? More or less? More or less than nominal. What would it be? Because of deflection. Again, let me repeat. If I want to remove some depth of material, some width of material, so I have some axial engagement, some radial engagement. If everything was perfectly rigid, it would remove that. Because the robot is not rigid, right? And there are forces acting, the robot will deflect, which means I'm going to remove less or more? Less because of deflection. The tool will be pushed away, right? So I measure lower forces, lower than nominal. So if I have measured the forces, this is what I'm measuring, using some sort of a sensor. I know what the relationship between force and deflection ought to be, or depth of cut should be. I can determine what is the depth of cut that corresponds to this force I measured. Okay? And if that depth, axial and radial depth, are less than what it should be, I can determine how much is the difference, and I can feed back. That's the basic idea. Okay? So what are the things I need to be able to do this? I need some way of measuring the forces. I need this model that relates the force to the instantaneous depths of cut. And then I need to just be able to solve for these. Okay? So, as long as you understand the basic idea, okay, don't worry about the mathematics of this. Okay? I'll show you some of the mathematics. But I don't want to confuse you more. I want you to just remember the basic idea. Force, deflection. It's F equals Kx is the idea that's being used here. All right? So I can compute it. I can do this. This illustration is simply saying the same thing that I described now. Okay? Now, how do I measure the force? Well, you have a rotating tool in milling, right? I mentioned last time, we mentioned a couple of times that there is a piezoelectric force dynamometer that exists. But in practice, you're machining a very large structure. We don't have such big sensors. Okay? Now, there are rotating tool dynamometers available too. They exist. Okay? And for robots, you can buy 4-stock sensors that you can mount on the end effector. They exist, 6-axis 4-stock sensors. But in this case, what we did, we actually had developed our own sensing technology. Okay? And this sensing technology is a very low-cost sensing technology, which is very non-intrusive. Non-intrusive because you're not modifying anything significant. You're not modifying the mass or the stiffness of the structure on which you're mounting the sensor. That is what you want to do, right? I want to sense something without modifying significantly its characteristics. So what is this sensor? This sensor is a thin film sensor. It's basically called polyvinylidene fluoride, PVDF. routinely used in many other applications. PVDF is a piezoelectric polymer film. It's the same principle as the other dynamometer that was referred to, piezoelectric dynamometer. It uses the principle of the piezoelectric effect, which means if I were to deform the sensor, right, I will generate a signal that is somehow related to the force that caused that deformation. So by measuring the change in deformation, I can estimate the force. That is the principle, right? These piezoelectric sensors, whether they are made out of quartz, which is what we use typically, but this one is a polymer film. It's a plastic film that behaves the same way, follows the same principle. It's very thin. So when I put it on a structure, it's like me taking a cellophane tape and attaching it. Very thin. That's all it is, right? And it's got very high bandwidth. It's very sensitive. It can measure displacements or strains on the order of, at frequencies of variations in strain up to 10 megahertz. That's huge, way more than I need, okay? In milling, the actual frequency, the highest frequency as it's cutting is typically, depending on the spindle speed that you're operating at, it's on the order of a few hundred hertz, okay? Few hundred hertz. Now, if you're doing very high-speed machining, maybe the harmonics may be a few thousand hertz, okay? Not tens of thousands of hertz, okay? So this can be used. And what you see here is that sensor. You're all familiar with strain gauges? Yeah, you at least heard about strain gauges. So think of this as a dynamic strain gauge. It's a dynamic strain gauge. I can create rosette structures. I can put these together in a form to measure different types of strains that the structure is being subjected to. This milling tool, as it's cutting, is being loaded. It is being stretched. It's being bent, right? It's being twisted instantaneously as it's cutting. So I want to be able to measure its bending strain. I want to be able to measure its torsional strain. I want to be able to measure its axial strain, right? If I can do that, which I can do using strain gauges, right? If I put the right configuration, then I can measure the changing strain and based on this piezoelectric principle, estimate the forces that are causing those strains as a function of time. That is the basic idea, okay? So what you see, and it's very cheap. I mean, okay, I have quoted this in dollars, but maybe in India it's even cheaper. I don't know, okay? So we took this film, attached it to this type of thing. We built our own electronics with wireless electronics, etc. That's mounted here in this, right? And you're able to transmit wirelessly, if you want, the forces, okay? So what you see here is the measurement in a milling operation using this type of a tool, sensor. So now I can put this tool on an end effector of a robot arm and it can measure as it's cutting. So now I have the ability to get the forces in time, right? That's one thing we needed for that strategy that I described, F equals Kx. I know F, right? I know K. I didn't tell you how, but K is known because if I know the joint stiffnesses, I can determine what the Cartesian stiffness is using forward kinematics, okay? And if you don't know what forward kinematics is, don't worry. It's basically, in robotics, allows you to relate joint level properties to Cartesian level properties, okay? That's all it does. The math is more involved, but let's not worry about it. Okay, I'll skip this. This is showing you how those sensor configurations are that allows me to measure the force I showed you, okay? It's not as important. Let's see if this is showing you on a milling machine using the sensor, actually, that can measure torque. You can measure torque, you can measure Fx, Fy, Fz. You can do all of those things with the sensor, okay? And this shows you measurement of the torque in a milling operation with that sensor. And the red is with a dynamometer. That is the gold standard. That is a tabletop quartz-based piezoelectric sensor that some of you mentioned, people use in research, but you can't put that on the robot arm. So this is showing you that using this thin film sensor, you can get similar performance or similar measurement characteristics as you can with that more expensive. That dynamometer can cost you $20,000 to $30,000. Okay, that's what it costs. All right. So I don't know how much that translates to, but maybe 2 lakhs or 3 lakhs of rupees, right? Whereas this sensor is $5 or maybe total $100 cost, which is about 8,000 rupees. Okay. Yes, or 9,000 rupees.
Can you please repeat it again? How do you use this PDF sensor in your work?
So the PVDF sensor is basically being used. What you see is the sensor here, right? So that sensor is here. It's mounted on the shank of the milling tool. It's attached to it. Now, what I have not shown you, and you can see here, it's attached here as well. Okay, this is slightly different configuration. It's, oriented a little differently. The number of these sensors, these films that are mounted, there's at least 3. Minimum 3 you need to separate out the different strains. Axial strains from torsional strains from bending strains. Just like a regular strain gauge, okay, which is called a rosette structure. If you want to use regular strain gauges and measure strains, then you have to build a Wheatstone bridge circuit to measure the strains and separate out the different strains. It's the same idea, but we are using 4 just to be safe. They are mounted on the periphery of the shank of the end mill, okay? And as the tool is rotating and subjected to forces that are changing during cutting, it is undergoing these strains. And these strains are being measured, right? And are being transmitted and converted into force. Does that make sense? At least conceptually it makes sense. All the math I'll skip, okay? We don't have time for it. As long as you understand that, then you're fine. All right, so now this is some more math, but please don't write down the equations. I don't want you to worry too much about that. Just understand what we are doing here. So this is the tool cutting, and there are some forces acting on it at some point in time. That's what this is showing during upmilling. It's possible through theory, actually, to model these forces in the X and Y directions. This is the average force in the X and Y directions. This is very well established. There's textbooks on it, okay, using analytical equations, but in this case, not explicitly modeling the material properties. Yesterday, I talked about modeling metal machining, trying to model everything down to the microstructure, okay? We are not doing that here, okay? We are modeling the geometry of interaction, the kinematics of the process, which is easy to do, the motion, and we are modeling essentially the geometry and kinematics precisely, okay? The rest, material properties are all in terms of these coefficients, K. These K values are like, think of them as calibration constants. Okay, that embodies the properties of the material, the tool material. So it's it can be calibrated experimentally, which avoids the need for all of that detailed modeling I talked about yesterday. Okay, so this is well established. You can find this in a book, right? These equations can be derived like this. What are these in terms of? They're in terms of geometry and the cutting parameters and these constants. So as long as I know which tool and workpiece material I'm using, I can calibrate this using a small number of experiments. I know these K values ahead of time. Therefore, if I know everything else, as it's rotating, I know the rotating angle of the tool, I can estimate what these average forces are. So these are analytical equations. But keep in mind, I showed you how to measure the left-hand side now using the sensor. The left-hand side of this equation, I can measure. And I can compute the average. So, and I know the cutting conditions. Well, I don't know, because of deflection, I don't know what is the actual depth of cut. I know the nominal, I just don't know because of deflection what it is, right? So the objective is to measure the left-hand side with that sensor and estimate from this equation the unknown quantities, which is the axial depth of cut and the radial depth of cut. That's the idea, all right? So this is what we do. We can do this, okay? In this case, we kept the axial depth constant, so you can only need to estimate one variable, okay, the radial depth. So if you're cutting like this, the tool is going like this along the side, it's going to deflect radially, so the radial depth of cut will change. Axial depth will change a little bit, but we are ignoring that change. So I will find the radial depth, right? Especially if the axial depth is small. And with robots to do machining, unlike machine tools which are much more rigid, you can't take very large cuts. So you're taking smaller axial depths anyway, okay? So you can estimate this A is the radial depth. You see this? Radial engagement between the tool and the workpiece is here. So I can estimate this by measuring the force and using these equations. Okay, so conceptually understand. It's like, what's all I'm doing? So I know the force, I know the engagements. Well, this A that I estimate in real time can be compared against what it should be, the depth that I've specified. And whatever is the difference, I can adjust for it, compensate for it. That's the feedback. I can make the robot move slightly back, right? So that it cuts closer to the desired value. That is the basic idea. All right, so this is showing you implementation of all of this. And again, I won't go into all the details. This took some effort to implement this in real time, right? And you can see here in machining, there is the robot actually cutting with the sensor. And let's see if I can play it again. And if you look here in the inset, it's cutting an aluminum piece. And these are the forces that are being measured in real time, okay? And it's being used to compensate, okay? Now, we implemented this to see how well we do. Does it improve my accuracy, right? Which accuracy is what I'm trying to improve? In this case, the radial depth of cut accuracy, right? Because I'm estimating only that using the sensor, and I'm compensating for it in real time. I'm making the robot move, right? So what this is showing you is if you think, imagine that this is actually showing you the measured wall location after machining. Remember, if you're doing a milling operation on the side, you create a step, right? You create something like this. Let's say this is the wall. That I cut, looking at from the end, right? Or cross section. So if my robot was perfectly rigid, this should be 90 degrees, right? The robot is not rigid. Even a machine tool is not perfect. The cutting tool is also not perfectly rigid in a machine tool. So there will be some variation, right? Now, the tool is fixed here, up here, right? The robot is here. The machine tool is here. It's like a cantilever beam. So because of that, what do you expect this wall to look like in reality? Okay, so it's going to deflect away, right, like this, right? Which means that I'm going to cut less here, and I'm going to cut more there. The radial depth will vary. Nominally, it should have been this, or let's say if this was the final wall, milled wall, so maybe I removed this much. Nominally, I was supposed to remove all of this material, but because of the deflection, I actually don't remove all of it. I only remove something like this. So this is the real wall. So this is, maybe we say, ideally milled wall is the white. This blue, the actual milled wall. Right? Does that make sense? So if I were to erase all of this, the white, so I have this error. This much error is there along the axial depth because of radial deflection. Think of a cantilever beam being deflected away. Cantilever beam is rigid where it's fixed, where it's in the spindle, and it's free at the end. So it's going to deflect away, right? Does that make sense? So what I'm showing you here is the measurements. This is showing you at some feed, if I perform this operation on a milling machine, a rigid, regular machine tool, the cut wall is almost perfectly straight. These are measurement points along the axial depth. Measuring points like this, right? Measuring here, so forth, right? Those are those points that you see. This is on a robot, okay? All of these are on a robot. You can see here what happens if I increase the feed, which means I increase the force. I'm removing more and more material. There'll be greater force, greater deflection, and clearly I have much greater error. This is 0. This point is 0. Okay, this is on a machine tool. Relative to a machine tool, the best I can do is here. This much error is there. If I increase the forces by increasing the cutting condition, it gets worse. You can see deflection is like this, right? That's what is happening. So, but this now, if I were to use feedback, remember, this is what I showed you. This is the highest feed, no feedback, no compensation. Now I apply compensation using the sensor, the estimating the A value, feeding it back, and you can see I reduced it substantially. There is still error. It's not as good as a machine tool, but I reduced it. It's closer to this machine tool result, rigid machine tool result. The idea is not to replace the machine tool. You can't use the machine tool in this application, but can I get this to be, a robot to be reasonably accurate so it can perform the operation because it's more flexible. I can do this on an assembly line for an aircraft structure, but I can't take a machine tool there. Okay? So yes, I'm willing to sacrifice some accuracy. Obviously, this level of accuracy is not required for this application. Then it works, right? But I'm able to improve the accuracy. Okay. So that is our first attempt. I won't go through this. This is showing you many things we have done, ways of compensating for errors, all kinds of things. Better modeling of the joint stiffness properties, velocity control, sensor fusion, all kinds of things, which I don't have time to go over anyway, right? So there's too many things going on there. So this is our system. Now, our latest version of the system is, this shows you the robot. You saw the video earlier on, right? You saw the spindle here. Now, what I just showed you is where we used a sensor to measure forces, indirectly estimate where is the tool in the cut, and then compensate. Wouldn't it be better? You know, how is it that we as humans are able to very quickly, if I want to grab this chalk, I did that. I want to pick this up, I did that, right? What's making me do this, right? Yeah, what is it? So my eyes, I have a set of eyes that observes where it is, communicates with my brain, and my brain basically actuates my arm to go pick it up, right? There's a closed loop system here, right? Now, if I have an analogous system, set of eyes, yesterday you guys saw on that, maybe they said they had a camera on the robot arm yesterday. I don't think they demonstrated it, but they want to be able to use that camera, right? So camera is not sufficiently accurate to do what we want to do here. Those cameras, the precision that you can be able to infer from cameras, it's okay for autonomous guided vehicles or driverless cars. You know, you're not trying to achieve hundreds of microns accuracy. As long as the car doesn't hit me, so it's a few millimeters away, no, that's good enough, right, for that application. But it's not good enough for a machining application. So we need a better set of eyes, okay? So what we have here is what is called a laser tracker. It is essentially has a laser and it looks at a target mounted on the robot and it's able to tell within few microns, okay, over a certain distance, the position, XYZ position of that robot. And it can also tell me the orientation of that robot. Okay, so this particular laser tracker, along with the target that you don't see, there's a black target here. This is the TMAC. It actually allows me to know the XYZ and alpha, beta, gamma, okay, the orientation of this robot in space relative to where this tracker is located. So it's a set of eyes observing the robot. Okay, if I can, and it can do that at fairly high frequencies. So now I don't have to indirectly estimate where is this tool in cut, right? Like I did with that thin film sensor. Instead, I look at this robot with the sensor and I know here's X, Y, Z and alpha, beta, gamma as a function of time. I can do that 1,000 times a second, okay? This is, of course, a very expensive instrument. And this is not applicable. No, you can't use this for, only for the kinds of applications for which we are designing, you can spend this kind of money, right? For aerospace type of applications where you're making very, very expensive parts and components, you can justify implementing this type of a sensor, okay? So we have this. This allows me to observe in real time where the robot is, using various transformations between where the robot is relative to this, where the end effector is relative to the base of the robot, etc. I can actually program and measure the real location, and I can compensate for it. Okay, that is the current way of doing it. All right, so this is showing you how we have done that, right? Now, there is a lot more to doing this. It's not as straightforward. So if you just walk away with an appreciation that this can be done, that's good enough. Because we don't have time, it'll take me, what I'm going to share here is work over 10 years that obviously cannot be summarized in a 1.5 hour lecture, right? So at a high level, I can do that. So we have a tracker. It's measuring the position of the robot. There is some real-time operating system that's running on a PC that's actually measuring the difference between where the robot needs to be and where it is, and taking the error and compensating for it, and commanding the robot to nudge here, nudge it there in real time, okay? And by doing so, this is essentially showing you using the robot to cut, in this case, fiberglass material, not a very strong material, not a very hard material, I should say, cutting a sinusoidal profile, which is a fairly complex profile, okay? Not very complex, but complex enough, which exercises various joints of the robot, right? And that's what, as I mentioned to you, with each pose of the robot, as it changes, the stiffness changes and errors change, etc. That's makes it complicated to machine using robots. So this is showing you measurement, okay, of the tooltip position of the robot, right? If I don't do any compensation, I don't use a laser tracker and I don't feed back anything. I program the robot and ask it to go. This is what happens, okay? When it's cutting. As it moves from left to right, this yellow and red is where errors are greater. You can see here, the average position error is about 0.4 millimeters. Still pretty good, but still large, right? Plus or minus 0.28 millimeters over this region, this length of space. This is not exhaustively looking at all positions in space that the robot can go to. Now, using this compensation method that I just described to you qualitatively, using the set of eyes, the 6 degree of freedom laser tracker, I can reduce that. You can see here the variation, there is some variation going from left to right along the sinusoidal path during machining, but the average position error is now 127 microns, 0.127 millimeters. From 0.4, I brought it down to 0.127. That's within the tolerance of what I would want to achieve for the kinds of applications I described, okay? So that's possible to do that. So that is one thing we did. All right. What are the other challenges? Well, I was cutting fiberglass, not a very strong material. So the forces are not going to be that large. So, dynamic vibration of the robot is not going to be that challenging. It won't be that significant, right? It could be, but it won't be as if you're cutting metal, for example, right? So, and a robot arm is not as stiff as a machine tool. So if I want to cut metal like aluminum, titanium, even composite structures potentially, you might encounter much larger forces and cause time-varying deflections, right, or vibration. Well, what is the challenge with why can't I do what I just did? You can, but the challenge is the dynamic stiffness of this robot. The static stiffness is one thing. I can take a robot to one point in space, push on it, I can do F equals kx and find the static stiffness. But dynamic stiffness, that is, if I take and excite the structure with an impulse, what happens to a typical mechanical system if you were to hit it with an impulse force? What do you expect? Suppose you take a pendulum. Let's take an example of a pendulum, basic physics, right? And I strike it. Displaces, yes, but what does it do? It oscillates, right? Effectively vibrates till it dies down eventually, right? So same thing robot arm will do. If you excite it, tap it somehow, think of during cutting, each time the tool enters, it is being excited. Impact loading. It's going to be excited and it's going to vibrate. Now, if you just do an impact, it'll vibrate at its natural frequency. For some of you may have done basic system dynamics. You learned about damped natural frequency, undamped natural frequency, and so forth. So it's typically damped. Most mechanical systems have some damping. So it will damp and eventually the vibrations will die down. The greater the damping, they'll die down sooner, right? Now, so if I want to know what is, and that the vibration characteristics change as a function of pose of the robot, right? And so what am I interested in when I say dynamic compliance? Well, because of that vibration, the actual displacement that it undergoes is a function of the frequency with which you excite the structure. So it's like resonance. In other words, if you're familiar with the resonance, that is, if I excite the structure at its natural frequency, it'll vibrate violently. So violently that you could actually break it, right? You don't want to do that. Every mechanical structure has a natural frequency, just like a beam, a cantilever beam. You take a cantilever beam, just do like that. Just tap it at the free end. It'll do this. It'll vibrate at its natural frequency and eventually die down, right? That's free vibration response. It's freely vibrating, right? When I'm cutting, it's forced vibration because I'm forcing it at some frequency, which the tool is engaging, disengaging, engaging, disengaging periodically. So it's like a forced vibration response, right? So I want to be able to describe this because then only I can see whether during milling, will this robot arm be like a cantilever beam? Will it vibrate? And how much will it vibrate? So I can suppress that vibration, right? That is my goal. So this is showing you a tapping of that milling tool, taking a hammer and tapping it. It's called an experimental modal analysis as a technique, right? That is used to determine what is called the natural frequency of the structure, right? And other properties like damping coefficient, natural frequency, stiffness, all of that you can determine. This is showing you the response, okay? This is showing you the response. I can describe this response in that pose of the robot as a second order system. So don't worry about the mathematics. This is showing you a Laplacian representation of that model. This is showing you that, it vibrates at this frequency. This is showing you the displacement as a function of frequency for this robot located in this pose. If I tap it, it's going to vibrate like that. At that frequency is what this plot tells you. This is its natural frequency in that pose. But because the configuration of the arm can change during machining, right? Machining some complex profile like my arm will change. The natural frequency may change all along, That doesn't happen in the machine tool, but it happens with the robot. So I need to know how this natural frequency changes all along its path in order for me to say, oh, how much will it vibrate as I keep cutting under these cutting conditions so that I can try to compensate, right? That knowledge I need in order to improve its accuracy. Yes?
More than compensation, is there any work going on to reduce the vibrations when external force is suddenly applied on a robotic arm?
Sure. So one is you could make your robot very stiff.
That will compensate the motion, right?
I'm sorry?
That will compensate the motion. We need more force to actuate it, right? Then the stiffness is more.
No, I don't follow. What do you mean? So I said you can make your robot more stiff.
When
Okay.
it is more stiff, it may lead to other kind of consequences,
Such as?
like more force needed or something.
The thing is, how will you make it stiffer? You have to make bigger links, bigger joints. Yes, that is expensive, and you will have a very massive machine, right? Yes, it will take more inertia. It has more inertia for you to move it. Yes, it is true, right? So this is not a very practical solution. Or you can somehow constrain the joints. You can reduce the number of joints. When you do that, you reduce its reach. Well, then why bother using a robot? Because I'm using a robot because it can reach many points in space easily. So those are some of the challenges. Or you could say, I'm going to cut very lightly. Okay, that's an option. But from a manufacturing standpoint, I want to produce things fast as long as I can, as much as I can. So that's why we want to try and find ways of compensating or suppressing, okay, the vibration. That's the reason. Because other solutions are more expensive to do. Like buying a bigger and stiffer robot. If you have money, you can buy that, right? That's the challenge. So this natural frequency is only for one pose. So I need at all other points in space too. There isn't a way to do this, okay? No manufacturer will give you, when you buy a robot, what it's going to be. So you have to build your own model. So this is showing you how we went about building knowledge of what the natural frequency of vibration, what the stiffness, etc. is at, let's say, 9 or whatever, 12 points in space. Okay, locations in space. 12 is just one, there are infinite positions that the robot can go to, but this is just developing the methodology. Okay, and we can estimate using such a model the stiffness, damping, and these kind of things. And we can build empirical models. So don't worry what this type of a model is. Think of it as a simple regression model. Okay. It is a regression model. It's called a Gaussian process regression. It's a different type of regression model. It is basically an interpolation. If I have, let's say I do experiments at 12 points, I know the natural frequency, right, at each of those points, like I told you, right, by fitting this second order system. I have 12 such natural frequencies corresponding, and actually more than 12, because at each of those points I excite in X, Y, and Z, 3 directions. Okay, so 3 times 12, 36. And I can also rotate the tool around that point, right? And I do that, I think 5 locations or something. So 36 times 5, orientations. So it gives me so many points. So I can take all of that data and interpolate and fit functions, regression functions that describe how the natural frequency changes as a function of location in space, how the damping ratio changes or damping coefficient changes as a function of location in space, how the stiffness changes as a function of location space. I can do this, okay? So what we do. Now, let's not worry about this. I think what's more important is that it shows that it is not constant. These things vary. If my arm is outstretched, intuitively, I already explained why that is the case, right? It is easy. If it's outstretched, the stiffness is not going to be as good. This stiffness is going to be better. Same idea. The data shows that, okay? But now I can fit a model. I can use that regression model to estimate. Hey, if I'm here, what is the stiffness? What is the damping, right? What is the natural frequency? I can determine that from this model. Okay, it's an empirical model. Now, okay, I don't want to confuse you a whole lot more. Let me skip that for the sake of, let me show you what you can do with this model. Okay, so let me show you what you can do with this model. So you can use this model to say, how will my robot vibrate when it is at this location in space, right? So this is basically showing you a robot at some position. It's like this versus like that, okay? These are the two positions. You can see this is outstretched. That's generally not a very good position, okay? It is less outstretched, closer to my base. Generally is a better position, okay? And using the model, I can predict what the natural frequency is corresponding in the X and Y directions, right? In the X, Y, and X, Z directions, because these are, what I'm doing here is actually, I am, in this case, this is a zoomed in view. This is showing you that the tool is moving in this direction and cutting in this direction, right? This is in the X direction, it's cutting. It's going to deflect in the Y direction, okay? It's going to deflect in the Y direction, normal to the direction of cutting. Here I am outstretched, but I am actually cutting in the Y direction. This red arrow showing in the Y direction. It's going to deflect normal to it in this direction, okay? So it shows you that you can actually predict the natural frequency behavior, okay? That's what these plots are. This is showing you what the frequency would be if I would actually do this in this pose and this position. Now what I've done here is I can take that model, I can take this regression models of stiffness, natural frequency, damping, and for those of you who understand system dynamics, like I don't know how many of you for a second order mechanical system are familiar, but right? Something like this, a second order system, mx double dot plus cx dot plus kx equals f of t, really, right? This is a function of time. So this is the forcing function, the cutting forces. It's going to call, this equation describes for a typical mechanical system, a second order differential equation, ordinary differential equation, that you can solve for x, how that x varies, okay? Which is the vibration, okay, in response to that forcing function. Well, this is actually showing you in these two positions, the actual vibration behavior, okay? Actual vibration behavior of the robot. This is when it's cutting in the X direction and vibration in the Y and Z directions, okay? The Z and Y directions, Z being the normal, Y being perpendicular to the feed direction, okay? The dashed line shows you what the average value, okay? So the stiffness is different. So the actual deflection, average magnitude of deflections are different. Now notice when it's now outstretched like this and I'm cutting in the Y direction. So it's outstretched like this, but I'm going in this direction, okay? No longer going in this direction. If I go in this direction, outstretched arm, it's going to be stiff, right? So that's the X direction. I'm going in the Y direction. So it turns out when I'm going in the Y direction, the vibration in the X direction, peak to valley is high. The reason it's high is because the natural frequency of the structure is quite high. And it so happens that the cutting conditions I have selected are close to the natural frequency. So it will cause resonance. So now I'm going to excite the structure at its natural frequency or very close to its natural frequency. It's going to vibrate violently. That is the reason why. Even though that X direction is stiffer, static stiffness is greater, right? It's stiffer in this direction. Because I am exciting the component of force acting in that direction is very close to its natural frequency, I'm going to excite it. Okay, that's what's happening. Using these models, the regression models, I can predict these displacements. I can say, oh, this is how much, this is really comparing prediction to measured to prediction. I can predict the displacements in the X, Y, and Z directions as a function of poles, okay? which is an advantage because now I know how much it's going to vibrate. I can try to do something about that if it's too much, using some sort of a control feedback, or I change the poles such that the stiffness is greater. It will not vibrate. I have several options. Okay, that is the idea. All right. Let me show you something else. And I realize not all of you have had control systems, controls. So you won't follow the math on this slide. But if I have these models that describe the dynamic behavior now, right, these regression models I talked about, from which I can predict the response, I can describe using this type of equation, I can predict the response. If I have this model, I can potentially design a feedback control system where I can minimize that vibration. Okay? And that is what we have tried to do. Now, the way we have done it is using called optimal control theory. This is a way to basically define a cost function, objective function, and minimize that objective function. In this case, which is the deviation from the nominal, I minimize that by varying something, right? In this case, I'm varying some gains in the control loop feedback loop, basically. So I realize some of this goes beyond what your background has prepared you for at this point. But I think just understand that there is a way to actually design a controller using such a model that can change the compensation amounts at different points along the path where I know how much it will vibrate and how it will vibrate because I have these models now. Okay? That is the idea. So let's skip the math. This is too much, in my opinion. Let's see what it does. Okay, here's the implementation of it. This is without any feedback. I'll explain to you what you're seeing here. What you're seeing here is, this is the end effector of the robot. I have zoomed in view, and I have mounted, what I have mounted there is a spinning, it's rotating, the spindle rotates. I have removed the cutting tool, and I have put a offset mass. I have put a mass here that is offset from the axis of rotation. So there is some eccentricity. So if I put a mass offset from the axis of rotation and spin it, I will apply centrifugal forces at some periodicity based on the rotation frequency. So I am actually applying a sinusoidal force of known magnitude and known frequency determined by the rotation frequency. Okay, that's the simplest type of excitation that I can provide, which I know what it is. In machining, you could argue you don't know exactly the forces. I mean, you can predict it, you can measure it, but for simplicity, here I am saying I'm going to excite the structure at this frequency, at this magnitude, amplitude of force. So that's what I am implementing. So I put this thing, offset mass, at the end of the robot arm, and I have spun it, and I have attached to it a thin rod here. This rod that you saw that was vibrating is the robot vibrating. It's attached to the robot in response to this sinusoidal excitation. Okay? So what you saw previously was how it vibrates when there is no compensation, no feedback compensation using this optimal control methodology, which accounts for what the vibration will be because I could predict the vibration, all the things that I talked about. So this is no feedback. Okay? You can see it's vibrating, correct? And it's vibrating at the same frequency as the excitation frequency. This is with feedback. It reduced the amplitude of vibration, you can see, right? If you didn't catch that, let's do it one more time. No feedback, pay attention to this wire. And now with feedback, then you can see how much it reduced. This is only at one pose, obviously, but I can do this at different poses along as the robot is moving. Get the idea, right? So this is one way to compensate for dynamic effects, right? So these are things, and this is now during the same kind of thing with feedback, without feedback. This is actually measuring the displacements. I showed you visually. Now I'm measuring it. with my laser tracker, which can measure and then it shows you how much I'm able to suppress. It's not zero. The pink is the reduced amount of vibration. The black is without the feedback, right? Now, what happens? This is at very high frequency. Now I'm close to resonance. That's why I'm unable to compensate. Okay, very well. There is a limit to how much I can compensate. Okay, that's what this is pointing to. Now, okay, you know what? Let's leave this. I'm not sure that is as important, but you saw this already. So this is during cutting. Now, forget about this. This video you already saw, but this is now doing machining, actual machining, and using that model, the same strategy, and seeing how much I can suppress. And you can see the pink represents the control feedback loop, the controlled cutting operation, using those models and the feedback gains that I have computed as it changes position. Okay, so you can minimize and suppress these vibrations, is what this suggests. Okay, so I thought I had more, but maybe I rushed through. I quit some things. But again, I see that not everybody has the kind of background required for some of these things that I'm talking about, but hopefully what I have conveyed to you is that industrial robots are not accurate enough for applications like machining. Out of the box, they are not, right? Unless you're doing it for very low accuracy applications. These robots are being used today for relatively low accuracy, or you're teaching it to go only to one point. Like in automotive, in spot welding, you see videos, you go to YouTube, you look up, you'll see videos of lots of robots doing spot welding in an automotive assembly line. Have been used for a number of years. And they program these robots to go there, and they do a very good job. They're zero force operations, really, spot welding type of operations. But when it comes to these kind of things that I'm talking about, much harder to do. That's why they don't do it, right? Especially if you're talking of making very accurate parts using these types of robots. Now, is there a need for it? Yes, certain industry sectors, aerospace and others, when you're doing very large structures, there is a need. There could be other applications too, where robots maybe, think of grinding and polishing. So when you talk about some of these operations are done manually today, okay? Even though people have built exoskeletons to try and, wear and tear of the human arm. Your arm can only, if you do this 8 hours a day, 5 days a week, for months and years, you won't last very long. Manually grinding, polishing by hand. That's an ideal application to use a machine to do it, right? But then that machine needs to be able to know. Humans do very well. Why? Because humans can see. And they have this excellent hand-eye coordination. And they are able to, they also are very dexterous. Robots are not as dexterous. But those are kind of applications like sanding, polishing for large structures or others that where you want to do, where robots can be used. And you do need accuracy, okay? Forces are less than milling. So what I'm trying to show you here is a challenging problem, right? That's what interests me. I want to do research on things I cannot do today. I want to solve those problems, right? So that is more important for me. Give me a second. Whereas from an industry application standpoint, there are some things that you can do already. So there are other applications where something like this would be very useful, okay? But, we don't know how to quantify the accuracy of robot arms very well still. But there are increasingly more applications that require robots to do more precise, let's say more accurate, I should say, not just precision. They are very precise in terms of repeatability, but not accurate enough. But there are more and more applications. If I can make them more accurate, they will be used. And there is justification, both cost-wise, efficiency-wise, to do that. Not to replace human beings, but the real reality is that in some countries that is an issue because they don't have people. But even in countries where there are people, there is value in doing that, because then you can free the human from doing difficult, laborious tasks, and then free them to do more intellectually challenging tasks, right? So there's a reason for that. Again, compensating is possible. I showed you some examples of it, compensating for the inaccuracy, but more work needs to be done. These things that I showed you are not something that manufacturers of robots will give you, right? They don't do that. You will have to do it on your own if you have to do this. But time will come when these kind of things will be more, let's say, built in. There's a lot of interest in using data-driven methods, machine learning methods to learn, things like, let's say, thermal errors. Temperature variations will cause the position of the robot arm to change. Can you monitor temperature variations, monitor the position, and build some sort of a model and use that model to compensate, right? For thermal expansion and contraction in a factory in a foundry, for example, where the temperature variations can be very large. Or wear and tear of the robot, progressive wear and tear. Obviously, if it is worn to the point that components have to be replaced, you have to replace it. But otherwise, you can simply use data-driven methods or machine learning type of methods to monitor degradation in the behavior of the robot, right? Just like you can do that for a machine tool or some other, system. All right, so I will stop there. So we have about 30 minutes or so for discussion, Q&A. Maybe this was even more than complicated stuff than yesterday. Yes, please, go ahead.
So this may not be in the scope of industrial robots, but I have seen parallel manipulators in robotic surgeries.
Mm-hmm.
So they are highly accurate, and doctors have been using them. So is there any chance of using that kind of, a concept for these applications?
I mean, parallel link manipulators have been used and tried actually back even in the 90s. There was a parallel link manipulator-based machine tools were built called hexapods. Commercially available machine tools were built actually back in the day for aerospace type of applications. But the challenge is that the work volume is reduced. And if you use those Stewart platform or parallel link manipulator type of structures, you curtail you can get better stiffness and maybe even accuracy over the work volume, but the work volume is not as large as a serial link manipulator. So they have their uses, but I am not aware of anybody necessarily using a parallel link manipulator for machining, even though people have tried it and even produced commercial grade, industry grade machine tools. I've seen them actually in the 90s, but I don't know of who is using them. There are things like there's something called flex picker. If you go online, you can do a Google search and you can find in YouTube flex picker, which is like a flexible parallel link manipulator arm for very rapidly, it'll actually do picking. So designed for agricultural picking, picking things from trees. That's a hard problem also, but those kind of applications, people have designed these things for. But yeah, so there are some advantages of those type of systems. If you think of, for those that don't know what he's talking about when he says parallel link manipulators, machine tools and robots are serial link manipulators. They're serially attached, like your arm, like one joint, link, wrist, right? So serial link. Parallel link manipulators are, if I take two joints like this and I do this, right? I can change the stiffness characteristics. And I'm just giving you a very simple example. They're more complicated than that. And where you see them like for example, if you've looked at flight simulators, if you've seen pictures or videos or online, you can go look up flight simulators where pilots train, right? Those flight simulators are all Stewart platforms. They are parallel link manipulators on which they can produce all kinds of orientations and motions. But they're not using for machining or anything, but they're using it to train pilots. So they're used for those types of applications. That concept is used, not for machining. At least I don't know of who's doing it today. People have tried it. Other questions? Was this too much over and above what you guys were thinking of? Yeah. I prepared this based on not knowing who the audience was. I thought they were all PhD students. So this is less I'm talking about stuff that we have actively worked on in research. So these were topics of PhD students who wrote their theses on, right? So not just textbook material. It's not. It's in research papers and not in textbooks. Well, so you mean to say how in terms of actual hardware? So if you look, okay, so I kind of glossed over it. So this is kind of the high-level architecture. So you have, just like you have, yesterday you showed us your setup, right? You have a Yasakawa robot, which has its own controller. So we have a KUKA robot, which has a KRC4 controller. The controller controls the motion of the robot. You can program it. But what we have done here is we have an external PC. The external PC is running a real-time operating system. This real-time operating system is called TwinCat. It's actually an industrial strength real-time operating system environment that you can run on a PC. So it creates a shell, a real-time shell. And it's from a German company called Beckhoff Automation, okay? Because KUKA is also German, originally German, so they're designed to communicate. You can actually communicate with the robot controller through a feature called RSI. RSI stands for Remote Sensor Interface, okay? And you can communicate with this robot every 4 milliseconds, nominally. So every 4 milliseconds, you can send it corrections to the nominally programmed path. That's one way of doing it. So you program, you say using the KUKA robot language or ROS or whatever you want to do. Typically using KUKA robot language, you can program it. The robot starts executing that, doing its own motion planning. And you're looking at it with the tracker and saying, oh, this is where it is. And this PC in the real-time operating and running the real-time operating system communicates with the tracker, right? And whatever the tracker sees as to where the robot is physically is communicated to this. This also has knowledge of the same program, nominally commanded program. So it compares the difference between where the robot is, according to the tracker, and where it should be at this time instant, determines the difference, and sends a correction using a PID type of a control law or using an optimal control law, like the one I showed you for vibration suppression, or any other control law. You can implement your own control laws. Send a correction command, okay? And that correction is sent every 4 milliseconds through RSI to the robot controller. This is like a black box. This is off-the-shelf robot, just like yours. You had to open it and put your current sensors and so forth. So we haven't messed with it. We want to demonstrate capabilities that somebody else can do themselves as well without opening up, the controller of the robot manufacturer. So, but they have provided an interface which allows us to make changes in real time, or quote unquote real time. There is a delay. Turns out there is a delay between 30 to 50 milliseconds at least, maybe sometimes greater depending on the robot. Yasakawa may be even greater actually, but I don't know. Somebody told me that it could be up to 200 millisecond delay. But yeah, I don't know. So it's about 2 milliseconds. But in our experience, it's somewhere between 30 milliseconds to 60 milliseconds. And but then you can make changes to this. That's one way. But we can also control this robot through this external, this is like an external control loop around an internal control loop, because the robot itself, controller has a control loop for position and velocity control. We don't have access to it because that's running at some tens of microseconds probably. The TwinCat itself is running at about millisecond, 1-2 milliseconds, clock rate. But we can also, instead of modifying an existing program that the robot controller is executing, we also have the ability to drive the robot entirely based on the tracker. So we can implement that. We have implemented that on our system, where the robot doesn't know what next command it needs to use to execute. It receives it directly from this control computer, external control computer. I think so. That's a good question. I think so. Maybe it has to. The thing is, they have some cards you need. EtherCAT is the communication system, kind of the bus that uses. So, to what extent Yasakawa controller? I'm sure Yasakawa controller has a mechanism like this. I don't know what it's called. You need to investigate. I know FANUC does. Right? FANUC has a similar thing. They call it some dynamic modification, dynamic path modification or something they call it. So Yasakawa probably has something similar. And you will have to look at whether that is compatible with TwinCat. ROS, unfortunately, is not a real-time, thing. It's great. I mean, it's flexible and it's very adaptable. It's open source and all that. But we started with ROS initially. But then our industry collaborators said, no, we want something that's industry grade. And so we switched to this. But there's a big learning curve. TwinCat is not easy. Oh, I didn't really go over that. Let's see if I have any information here. So we designed our own electronics or circuit board with a microcontroller, with a microcontroller on it, and onboard memory and onboard battery. And that's all in this housing that you see here. We have documented it in the papers. Yeah, I can point you to those papers, okay? And then, you see our first version of it here, right? Then we have actually another version which we did on a Siemens project, where we actually took all the electronics which we had done manually. My student actually had put the printed circuit board himself, and a wireless transmitter and a receiver as well that you need. But we got it all prepared as a flexible printed circuit board, so that can be simply wrapped around and attached to the tool holder. So it becomes part of the tool holder. We did that for a boring bar project, actually, for Siemens. So that also is published. You can look at it a few years back. That'll give you some idea of how we did that, actually.
Sir, I have a doubt, sir.
Yes.
Sir, you are saying that robotics CNC machines are more accurate than robotic machines. So in CNC machines like 12 axis, 10, 12 axis machines, they will also vibrate here. So
Sure.
they are also like a cantilever beam only. So the vibrations will affect the accuracy of the machine.
Yeah, absolutely. There's vibration in machine tools too. This is much more compliant than a machine tool. That's the point I'm making.
Okay, so
Yeah, it's not that you don't have vibrations in machine tools. What you don't have, you have machine vibrations in machine tools, you have chatter vibrations, you have much more severe chatter vibrations in a compliant arm like this, actually. Okay, so this is more susceptible to it. Okay, the other thing is, the other difference is that in a machine tool, the change in compliance characteristics of the robot over its workspace is negligible, it's minimal. So it's more or less, you can assume it to be constant, okay, its stiffness characteristics with pose, if you will, even on a CNC milling machine. You can't do that here. So its stiffness changes with pose. That's well known and well established, right? Significantly enough that its static deflection properties, static compliance, and dynamic behavior changes. That is very different than a CNC machine tool, including your dual spindle machines or whatever. Now, there are machine tools where people will actually add a robot arm to the end effect, to the spindle. Then, of course, you're introducing more significant compliance, potentially. There are such systems I've seen, but even then, the entire structure of the CNC machine tool is so much stiffer. That's not the case here. Keep in mind, there you have linear slides and guideways, much stiffer. Your revolute joints here. Yeah.
So is medical robots are more accurate than industrial robots?
Medical robots. Look, unless there are fewer degrees of freedom robots, but if there are 6 degrees of freedom robots, like, for surgical robots, that's something.
Surgical robots.
Yeah, surgical robots. They teach those robots. I mean, they're guided, the vision guided, and the accuracies, you would think the accuracy requirements, yes, they need to be sufficiently accurate, but I don't believe the accuracies, human body variations probably are much more in terms of shape and location and size, that I don't think you're demanding accuracies on the order of 200 microns, 250 microns in a surgical environment. Plus, a surgeon is guiding the robot, right? Essentially, the surgeon basically identifies where exactly the robot needs to go and then programs the robot to perform the actual surgery, right?
So, but still they place a backslash or wear and tear of the
Sure,
robots.
of course. Yeah, of course. Yeah. That's true for any robot or any machine. Indeed. Yeah. I don't have personal experience with those type of surgical robots, but I would be surprised that if they're not experiencing the kind of loads here. Of course, you can do drilling and you can do things like that, but you're cutting through, I think the forces are probably much less. Yes, you're cutting through bone, potentially you're cutting through some composite material, right? Human body is like a composite material. Bone is probably the hardest substance that it'll actually encounter. But I don't believe that you need the same type of accuracies there. And also, they're not totally autonomous in the sense that they're not just, you don't just program them and go. I wouldn't want that type of a machine operating on my body. I want it operating under the expert guidance of a expert surgeon. Yeah, but I don't have numbers, to be honest with you, right? In terms of accuracy for those robots. I mean, nobody quotes accuracy for robots. You have to characterize it.
Thank you, sir.
Yeah. No questions today from the undergraduates. This is probably too much for some of you. So again, apologize. But nevertheless, hopefully you at least got an appreciation for the challenges in using industrial robots for applications for which you can't use them today, and potential ways of addressing it, even if you didn't understand all the details. Right? It's okay if you didn't understand all of the control theory or you know, all of the mathematics associated behind the scenes that is there. But if you understand this much, I think this is okay. Yes.
I've seen robot cladding.
Mhm. Yes. Yes.
The difficulties that we generally see during machining,
Yeah.
they are not that prevalent in cladding, sir. Are they?
Say that again.
I mean,
Oh.
the accuracy levels that
Yeah.
are required during machining,
Yeah.
are they not required for cladding?
But you know, if you're using something like a deposition process,
deposition
like or even a welding process like a GMAW,
Yeah.
the variability in that process, the deposition itself is significant.
Okay.
You know, you're talking of millimeters probably in terms of variability in bead geometry, right? Whereas in machining, you need, you know, we're talking of sub-millimeter, you know, accuracies. So the process variability there itself is high. If you're just doing, you know, maybe laser welding a little less than in fusion welding, arc welding processes. But, you know, I don't think they're as, you know, it's not, again, it also depends on how you're going to control that robot. If you're going to teach the robot, which is how many people in industry still do it, they can do using offline programming too. But you're going to teach the robot manually using a teach pendant, it'll keep doing that over and over again within a repeatability that's like on the order of 50 to 80 microns. And that's good enough. That's plenty, actually. That's the best you can do with those robots, right? But the actual process variability is much more than that. So repeatability of 50 to 80 microns is sufficiently accurate. And you're not dealing with forces, right? Like you're dealing with machining. So you're not dealing with the compliance issues. You may be dealing with kinematic errors, but depends on how big a bead, long a bead you're actually depositing, right? So if you're welding very large structures using a robot, then you would have to be mindful of the kinematic errors and the buildup. Yeah. And you have to somehow compensate for it, either through calibration. So better calibration is one way to do that. And again, the calibration also, even the best calibrated robots, like I said, calibration will give you something close to a millimeter or a little less than a millimeter, right? Maybe 700-800 microns accuracy, positional accuracy. If that's good enough for your application, it's probably good enough for the welding application, then it's okay. Yeah. Does that answer your question?
So you, in one particular, I think it's wherein you offsetted the workpiece, right, from the axis, and then you found out the vibration.
Yeah. After
that, with feedback, you reduce the vibe. I'm asking, like, why did you offset the workpiece?
Yeah. So this is the one you're referring to, right? This
Yes.
video where
Yes.
you have an offset mass spinning around the axis of the spindle. So it's an eccentric motion, right? You have an offset mass. Mass is hanging away from the axis of rotation, and you're spinning it at some frequency. So you effectively, there's a periodic excitation that you're subjecting it to, and it's sinusoidal. Pure sinusoidal excitation of a certain amplitude and frequency, which you know. I've designed the mass. I know the rotation frequency. So I can describe this as y equals this a sine omega t. I know what omega is. I know a, amplitude, right? So it is essentially a prescribed forcing function where I know what the forcing function is explicitly. Mathematically, I can describe it. So I can test how well my control algorithm, feedback control algorithm works. The reason to do this, as opposed to, we also did machining. In machining and milling, it's not a pure sinusoidal excitation. It's a periodic excitation. It is like a Fourier series, like a superposition of different frequencies. So it's not as simple as simply y equals a sine omega t type of excitation. So to keep it simple, we did this, okay? And by doing so, what we did, as you can see, without feedback, this wire is vibrating quite a bit. The moment the feedback kicks in, which knows what the forcing function is, it reduces the vibration, right? And this is at one pose of the robot only. You can do this all along there, which is what this machining experiment showed. Here, this is what I showed you. This is really during machining. You can't eliminate it completely. The pink shows you the reduced vibration. You're suppressing the vibration, in the two directions here, when the robot is here versus where the robot is a bit more outstretched. Because I know what the dynamic properties of the robot are in those poses, I can account for it and design compensations in my control algorithm to minimize this. But you understand why I was doing that offset,
Yes.
right? It's just to keep my excitation function mathematically pure, simple, but known ahead of time. That's all.
Also, sir, you talked about series link and parallel link
Mm-hmm.
joining two
Yes.
arms or something. Wouldn't that be more like comparatively more stiffer than a single arm?
You mean parallel link would be stiffer than the serial link? Indeed. That's one of the reasons why parallel link mechanisms are used. But the challenge with that is then your work volume reduces. So yes, if you have a small work volume, you have these multiple links connecting, parallel links that connect and produce the motion. You can get greater stiffnesses, but then you don't have the freedom of going. The reach of this robot is huge. You're talking of 1.5 meters or more, 2 meters. You won't have that with that type of a system. Okay? That's those are some of the pros and cons. Yes. Yeah, of the workpiece. Yes.
Yes.
Mhm.
So, how do you think this robotic systems for milling applications will be economically feasible? And how do you see where it can be applied in the coming years?
Well, changing dynamics of the workpiece happens even in machine tools, right?
No, for the robot.
Yeah, but what is the reason? The changing dynamics for the robot is because of the way it's configured. It's because of the configuration changes, the dynamics changes, right?
Yeah, but due to the wear and tear.
Wear and tear.
Yes.
Wear and tear. Well, any mechanical system will undergo wear and tear, including machine tools, right? So they have to be serviced, they have to be recalibrated, and they have to be repaired. So I don't think a robot is any different. Robots have been used in automotive industry day in and day out, right? For welding in. So they're moving very fast. And so they do undergo wear and tear. So I don't believe that is what is preventing use of these robots. I think what I was talking about is lack of our knowledge of accuracy of the robot, and also how do you ensure desired level of accuracy, positioning accuracy. And if you can achieve the desired levels of accuracy that we were targeting, then you can use them for applications that you don't use them today for. Like I said, machining for aerospace applications, where it's easier for me to put the spindle and the tool on the robot arm and take it on, let's say, your mobile platform that you had, right? In fact, Airbus has tried something like this. In EU, there's a project where they put a big, like a KUKA arm like this. This one is a 500 kilogram payload robot. They put something bigger than this, like a 1,000 kilogram payload robot, on a large mobile platform, and essentially tested the idea of doing machining of aircraft structures, trimming, hole drilling, etc., using that. So I think the aerospace industry, I would expect, would be the earliest adopters of some of these things. Other industries, perhaps the nuclear industry, again, because of safety hazards of servicing, maintaining nuclear reactors, repairing. That's where robots get used to, right? Because humans, you have to shut down your reactor. It's not a simple task. And so if you can send a robot in to do the task with vision and everything else like you are trying to do, that'd be an option. So I anticipate that those are the industry segments that will drive, including anybody who makes very large things, shipbuilding, those kind of things. I think where the flexibility and the reach of these such machines is an advantage. I expect they are the ones, if you get them to be accurate enough, they'll use them for more things than they currently use.
Sir, I have a doubt, sir. In the slide you showed, you have made use of the single hammer test to model the system. But in actual case, there will be a continuous force which will be acting on the cutter. And also it will be varying with time, sir.
Correct.
How do we model such system?
So that equation can model that.
Yes, sir.
Okay. But I need to know what M is, what C is, what K is.
Yes,
right?
sir.
I also need to know what F of T is. Right?
Yes, sir.
So what I'm trying to find is its basic properties, right? So for example, what I was trying to tell you, let's go back to that slide. Okay, yeah. So, this is the impact hammer thing that you talked about. The purpose of doing this is to know what the basic vibrational properties, free vibration properties of that structure are. This is standard. Experimental model analysis is a standard technique, right? It is not to simulate what happens during cutting, okay? This is to know what is the basic dynamic property of this mechanical system. So you do that by exciting the structure using an impact hammer. Gives you the free vibration response. In this case, the damped free vibration response, right? So, and where I'm making an approximation is in this particular case, I am basically saying that, look, I can describe its free vibration response based on only the first mode of excitation. This is a complex structure. In reality, when you excite it, it'll not only vibrate at this frequency, there will be some other frequencies too. I didn't show you, but there are other peaks that may be excited. So to describe its true frequency response function, I need to model all of them. But most of the energy, okay, associated with that vibration is contained here, the highest peak. So I'm approximating its dynamic behavior by that one mode that will get excited. I'm saying that if I somehow excite this, even if it is a machining force that's varying, time varying force, which is the case, then of course that would be like a forced vibration. But if that frequency of force variation, F of T, is close to this frequency, it's going to excite at this frequency, right? It's going to excite the structure at that frequency. So if I know this, then whatever the forcing function is, will allow me, now maybe I'm operating here, I'm exciting the extra machining forces varying at this frequency, far away from this, in which case I should not have much displacement at all. My model will say that, because this model says, oh, at this 950 hertz, amplitude of vibration is negligible. The model will say it. Does that answer your question?
Yes, sir. One more question, sir. Suppose, let's say you observe the system is under the natural frequency. The frequency of the system is matching its natural frequency.
Yeah.
You have got the feedback to control it, sir. What parameters will be adjusted so as to control the make the frequency not match with this natural frequency?
The easiest way to do that is to actually change your cutting spindle speed such that you make it much higher, far away from, so you change the F of T, the time variation of F of T, the frequency content of F of T, the forcing function, to be far away from the resonant frequency of the structure. That's the easiest solution, if you can do it. That is to change the spindle speed and move it away That's the simplest solution, right? If you're very close to the resonant frequency of the structure, there is a limit to how much you can actually suppress. You can't do much. I mean, the structure will vibrate, okay? And this is what I was showing. In this case, the spindle speed is 1440 RPM. My control loop is unable to do much because the bandwidth of my control loop is only up to about 24 hertz. I cannot do a whole lot. I can't force the robot to move as fast. There's the inertia of the system, you know. So I need some other way. But robots, it turns out, the worst vibration behavior. Most robots have natural frequencies somewhere from 5 hertz to less than 20 hertz. Typically 5 to 11, 12 hertz. That's where, if you excite them, and those are easy enough to excite, that's why they'll vibrate a lot. The higher modes, we don't worry too much about. Does that answer your question? The easiest solution would be change your spindle speed. Okay? Make it far away from the resonant frequency of the structure if you know what it is.
Yes, sir. Sir, one more question, sir. You told that the robot manufacturers won't be giving these sort of data. So if we
Correct.
have a robotic system for a company, so the company has to calibrate its robotic system so as to automate that.
Correct.
So it goes for every company. So there cannot be a single stop solution for all the robots to make it happen, sir. Right. So what I felt was, you told that it can be applied more to the aerospace industry because of the huge size of the components in which it is being machined. But historically, you can say that aerospace industry is like, it is well established, and they can have the necessary machineries to machine the aerospace components rather than to go in a robotic components. Because moreover, it is also having problems of the compliance, and also the dimensional tolerance is not so good, sir. But the same system can be applied on a small scale industry, which continuously keeps on shifting its products and the product chain. So I feel that it has more applications than in the aerospace industry.
No, you're right that in industrial environments characterized by high product mix, right? And rapid changes in product mix because of changing demand, you need a more flexible manufacturing system, which can be reprogrammed easily, repurposed easily, which robots certainly provide you one option. But it depends what you're making. You know, again, the reason the aerospace industry is driving some of these type of technology developments, why they're interested, I guess I didn't do a good enough job of clarifying that for you. But the reason is, as I said, assembly processes in aerospace, are very time consuming and they're laborious. You order a plane today, you'll be lucky if you get it in 4 years, right? Why? Right? Because most of these aircraft manufacturers have backlogs of 2,000-3,000 planes. They cannot produce. It's not like automotive manufacturing, mass production, right? I mean, these are very complex systems, take a long time. So they want flexibility. They're dealing with these very large structures. And the cost of machine tools for machining those types of structures are millions of dollars. And once they spend that, they occupy huge amount of space, and they are not going to get rid of it tomorrow easily. Okay, so those are some of the reasons that aerospace is driving it, and that they can benefit from speeding up and making. There are many other applications in aerospace, including assembling cabling in an aircraft. Right now, humans have to get in there to put in bundles of cables in an airframe structure. It's very difficult to automate that when you're dealing with those type of parts. So, but yes, I mean, there could be other scenarios like you mentioned, where you have high product mix, where as long as you can justify, these robots can be sufficiently accurate for their applications. Yeah, I don't see why not. I don't see why not.
Thank you, sir.
Sir,
Yeah.
is there any, like, instead of doing contact conventional machining, is there a way to accommodate the robot with a, advanced manufacturing system which is non-contact based?
Like a laser?
Yeah, laser or water jet,
Sure.
something like that.
Indeed. I mean, people are doing 3D printing with robots, right? Using the wire arc additive manufacturing process is a good example of it, where they put a MIG welder or a gas metal arc welding torch on the end effector and do deposition, right? Now, so for subtractive manufacturing is what you're talking about. So you could use laser, you could put a laser, but again, material removal rates are going to be where, and you need a very powerful laser, and very powerful laser means you're dealing with heat affected zones, thermal damage, and those kind of things. If you're going to rely on ablation or vaporization, ablation as the means to produce features. So, but yes, you can reduce the force, right? Or eliminate it.
If you are talking about doing machining in about tolerance with microns, then maybe.
I'm talking
Yes.
about on the order of less than half a millimeter. 0.5 to 0.25, 0.2 to 0.5 millimeters, or even less. Yeah. For certain things, you indeed can use lasers. But again, I think, again, you have to be mindful of some of the
Not just
other issues.
lasers, sir, any other method.
I'm sorry?
Not just lasers.
Yeah.
It includes like any other manufacturing process, like wire EDM.
Such
or
as what? Wire EDM? Well,
Maybe.
wire EDM is going to be very slow.
So,
And plus, you're talking of a dielectric medium you need, right?
maybe we can do it as a finishing process or something like that.
I'm sorry?
Maybe we can do that as a finishing process, or maybe to get
Maybe.
better accuracy.
Maybe. I mean,
Not-
it depends.
Uh,
It depends on what it is. I'm thinking in terms of aerospace structures, and I'm wondering, okay, how would I use wire EDM?
not wire.
Not wire
Maybe.
EDM, it won't work.
Water jet, maybe.
Water jet people do with robots.
Yeah.
They do that already. Yeah. For composite materials, you can. Yeah. But again, there are tapering issues and other types of issues with water jet too, right? So, but indeed, it depends on the application again. I'm not suggesting that it has to be machining only. But none of the other issues I talked about. Maybe the compliance issue can be minimized by reducing forces. Kinematic errors, those other errors are still the pose-dependent variation in accuracy. All that still apply, even there.
Understood.
Yeah.
Thank you.